Good morning again, also from me. Now, Travis and David have already talked about the huge investments that have been made already to make Android capable to tackle a very diverse range of businesses, starting from manufacturing, down the line all the way to financial services. But what it also means is that Android, as a platform, is exposed to an extremely diverse set of data, of information that's actually on the device. Starting, for example, with customer records, going on to confidential IP or even sales forecasts. Luckily, Android, all the security measures that have been built into Android are not just for enterprise. They are, of course, also applicable to all the customer and user cases as well. And Android has been exposed to that for a long time. Customers and users use Android already to process their medical data, to use it for financial transactions. And so all that wide range of data that's on devices needs to be protected. That means that on my team, we think about security and privacy first. There are a large number of potential threats that could apply to a mobile device. And in this talk, I'd like to be fairly systematic about it and structure that in three different main areas. There are first and foremost threats to the user, because users are the first and last line of defense to any security posture of a system. It is part of a mobile device that, by definition, they can be lost pretty easily. So we see that in practice, of course. Devices get lost. And the first thing we need to make sure is that only authorized users are actually allowed to use those devices. Secondly, and this is probably the one that picks up most of the media attention, there is obviously the potential to get malware on device. So I'll talk more about what we do to prevent what we call potentially harmful applications, or PHA, from being installed on end-user devices, or enterprise devices in this case. And thirdly, the platform itself is obviously also not immune to bugs. And this is where we put in a lot of effort to make sure that the platform itself can defend itself from any of those potential vulnerabilities that may exist. So let's start with end user, with the user-based threats that we might face. And as mentioned, the first task here is to make sure that only authorized users, owners or associated users of that device are actually able to use it. And that starts with a secure lock screen. For Android Enterprise, it is possible to define the complexity or to enforce the complexity of this lock screen with EMM policies. Additionally, and this has already been hinted already, we use hardware-based verification of those knowledge factors that can go into the lock screen, as well as fingerprint access, actually, to make sure that brute force offline attacks are not possible. What we enforce, and that started actually with Android 7, Android Nougat already, is that a trusted execution environment, a TE, has to be used to verify PIN codes, passwords, patterns, or fingerprints to make sure that a unique, device-specific unique key is tied together with that user knowledge factor to make sure that only on device this key derivation, the verification, can actually happen. In Android 8, in Oreo, that was extended by not only allowing to use a trusted execution environment on the main processor, but also supporting tamper-resistant hardware, separate security chips to make it even harder to mount hardware-based attacks. For Android Enterprise, this is actually a recommended feature for devices to implement. Now, after making sure that the device can only be used by authorized users, we encrypt all data that's on device. And that actually started with Android 5, where full disk encryption was already being mandated based on standard Linux kernel mechanisms that are in place. Android 7 strengthened this device encryption by mandating use of standard AES instead of other ciphers and introducing file-based encryption to give more flexibility. Additionally, in version 7, Nougat, we also introduced the capability to use different cryptographic keys for the personal profile versus the work profile to even better separate those two sides on the same device. And with Android 8, Oreo, we added another feature called key injection, which instructs the Linux kernel to actually remove keys from memory when the work profile is being disabled. Again, making it ever harder to leak data off device. Now, I would like to spend a few more minutes to talk about these protections that are hardware-based, because this is part of the very important security posture that a modern Android device brings. What you have probably seen in the past is talk about trusted execution environments, which is like a separate part on the main system processor, and that has already been used for quite a while for lock screen verification and for key derivation. Now, this is new with Android 8. We added platform support for what we call tamper-resistant hardware, most commonly implemented in the form of embedded secure elements, separate, certified crypto coprocessors that are on device that are, as mentioned, already being used for verifying lock screen. And the Pixel 2 device, Pixel 2 and Pixel 2 XL, shipped in 2017, already shipped with this feature enabled. Now what's new, and this is a bit of a sneak peek there for Android P, we are finalizing this as we speak, finalizing the specifications, is that we will now be able to use the tamper-resistant hardware also, so not only for lock screen verification, but also for storing, creating, and using cryptographic keys bound to that specific trusted hardware component. Now, finally, it's also important to make sure that any vulnerabilities that might exist in earlier versions, that might not have been patched in earlier versions of the operating system, cannot be used to leak those cryptographic keys off the device and therefore decrypt the data that might be on it. So what was already introduced earlier is called version binding, making sure that those cryptographic keys on a TE or the tamper-resistant hardware can only be used starting with a specific security patch level for that operating system release. And we also increased that guarantee with Android 8 by adding rollback prevention, making sure that on locked devices, the operating system itself cannot actually be rolled back to a previous, potentially less secure version. Now, I think we've already made clear that modern Android devices are quite secure in verifying that only authorized users can actually use them. I would like to change gears a little and move on now to what we can already do to make sure that those potentially harmful applications, PHA, will not end up on user devices, enterprise-managed user devices, to potentially exfiltrate data or otherwise attack those. Google Play Protect, already mentioned, was introduced last year, and again, that's the nice thing about it, it's not just for enterprise, it's for everybody using Android. Google Play Protect combines Google's world-leading knowledge on machine learning to the problem of recognizing, analyzing potentially harmful applications. So Google Play Protect server-side is able to scan all the apps that are on the Play Store, and this has been extended by what we call the Verify Apps feature to also scan apps that have not been installed through Google Play itself. So apps that are installed, that are side-loaded on the device itself, can, with user consent, enforced by enterprise policies if necessary, can be scanned as well, can be put to the same kind of rigor that we have for apps that are on Google Play Store. Now, detecting apps, detecting potentially harmful applications, detecting malware, is only one side of the coin. The second part would be remediation, and that's obviously possible on Google Play. Anything that we detect that might be harmful can be removed from Play, will be removed from Play. Again, with user consent, this is also, or enforced by an EMM policy, this is also possible on apps that were not installed from Play. So Verify Apps on the device, when it detects PHA, can also forcibly remove that from devices to actually mitigate applications that were only detected later in the field. Now, the impact of Google Play Protect is pretty clear from the data. We rapidly reduce the malware rates for applications installed from Play, and they are now, as you can see here, below 0.01%. Even more rapidly, actually, we are able to reduce the rates of software that's installed off Play, that's installed from other sources, that's side-loaded on devices, which has now, as you can see here, gone below 1% as well. This is through the use of the Verify Apps feature on the device itself. We continue to invest here to ensure that users all over the world have a safe application experience. Now, if you simply go by media reports, if you go by headlines, you might think that Android is riddled with malware, while other platforms are not. Other platforms are completely safe. I'm hesitant to comment on that, and this is why we rely on objective data by, in this case, Symantec, where they actually found that malware rates on another platform, on iOS, tripled in the last 2 quarters, or in 2017, while, as you saw on the previous slide, they actually, they actually improved on Android. So perception of security, as portrayed in media headlines, does not always line up with data that we actually have. Now, all those tools are available to app developers as well. There are APIs that can be used to trigger Verify Apps. There are APIs that we call the, that we call the Safety Net Attestation API that allows apps to programmatically verify if a device is in a certified state or not. Now, combined with Verified Boot, which I will go into a little bit of more detail later on, that can actually give remote guarantees to to applications running server-side that devices, the client devices, are in good state. Combine that with the use of safe browsing, where apps calling into URLs can actually make sure, using those APIs, that those URLs are not known to Google to be potentially harmful as well. And we have a very complete picture of APIs for applications to use here. Now, what we can also do here is, even if, and this is the first if here, as you can see, malware install rates are already pretty low. But even if malware makes it on device, the core platform adds isolation, or what we call app sandboxing, to make sure that apps that are potentially harmful cannot directly access other apps' data or system data or even attack the platform itself. Broadly speaking, what happens on Android, and this has been in there since the start, is that every single application being installed on an Android device, upon installation, will be installed with a uniquely generated dynamic user ID. Apps, by default, can only access resources that are under their own user ID, so their own data, their own directories. There are mechanisms for applications to share some data if they need to, but otherwise, if a single app wants to escape this tight sandbox, it will need to do so using permissions. Now, and this is, I think, the core fundament of the whole Android enterprise story, is that we have introduced the work profile. With work profile, that separation goes even deeper, because that separation means that those Android apps installed on the work profile end up in a completely different space of user IDs. So not only are apps isolated between themselves, but apps installed in the work profile are further isolated by being in a separate space. That work profile, as mentioned earlier when I talked about encryption, is also encrypted with a completely separate key. So on all devices using file-based encryption, there is a separate key for the set of apps installed on the work profile than those apps installed on the personal profile. In Android 8, we allowed for work profiles to run on fully managed devices. From an API point of view, that means that you can use both the device owner and the profile owner on the same device. For other installations, it's obviously possible to only use a work profile, to only use a profile owner, and therefore only give the EMM control over the work part of the phone and not over the whole device. We give this option, we give to all our customers, we give to all our partners, and together with the enterprise team, let you decide which of those options is better suited for your deployments. But let's change gears a little again here. Now we've talked about making sure that only authorized users can actually use the device in a way that's intended. Now, we also talked about making sure that malware does not easily, at least, reach the end user device. I would now like to spend a little bit more time, actually, on what we can do to make sure that the platform itself is hardened against such vulnerabilities. Also, just going by media reports, there's always been that pretty clear statement, that pretty clear perception that Android patching is one of the most problematic issues of the whole Android ecosystem. And yes, honestly, that used to be true. But the story is changing here as well. Together with many partners, we have now improved year over year the patch rate by 30%, meaning that in 2017, 1 billion devices in the field actively received security patches. Together with our carrier partners, many of whom are actually in the room, we have managed to bring the time from the first release of a patch until it hits those end-user devices down to typically below 1 week. And with this, I would also like to refer back to Android Enterprise Recommended, where all those devices that are in the list of Android Enterprise Recommended devices have to sign up for mandatory 90-day patch guarantees. So at a maximum, we allow them to take 90 days to roll out patches. We recommend 30 days, and all of that for at least 3 years, which gives a significantly more consistent patch story for all those devices that are signed up for the Enterprise Recommended program. Now, again, even if a device is not patched, then that is not the full story. Even if a device is not patched to the latest security patch level, does not necessarily mean that that device is actually insecure. And that is because we take an approach of limiting the attack surface on the device itself in order to mitigate that the next piece of malware or the next potential bug may not actually be problematic from a security point of view. To put it in slightly different words, our defense in-depth approach that we take on the platform side means that bugs that will exist in probably all software in existence do not necessarily have to become vulnerabilities. And I would like to take the next section here to run through those different security measures that are in place in the Android platform, that have been in place for many years already, and that are strengthened with every single Android Desert release to make sure that bugs do not have to be vulnerabilities. The first is the Linux kernel itself. Outside code that is executed on a trusted execution environment, on a TE, or the temper-resistant hardware that we introduced recently, security starts with the Linux kernel on Android. Everything's based on the Linux kernel. And as of Android 4.4, that is like ancient history at this time already, we started to mandate the use of SC-Linux mandatory access control policies and put them into enforcing mode. So even if a process managed to gain temporary root exploits, managed to gain temporary root privileges, that does not mean that that process can actually break out of its sandbox, because that sandbox is enforced on a very low, very fundamental level on the Linux kernel using SC-Linux. And this is already quite deep into hypothetical land. So assuming that A, malware gets installed on the device, B, malware actually manages to exploit a bug, a vulnerability that has not been patched on the operating system release currently running on the device. Then those two already have to be fulfilled. Then SC-Linux policies come into play and make sure that even those will not be able to access other apps data will not be able to directly interact with the system hopefully not in a harmful way here. Now, what has already been announced last year, we are quite excited about that, is Project Treble, which I think you're mostly familiar with, is the separation put in place to have what we call a hardware abstraction layer, a HAL, in between the kernel drivers and operating system components. Treble is important for a number of reasons, one being that it makes updates a lot easier. And we've already seen the impact that Treble has had on patch cycles. So Treble makes it easier by decoupling those two layers, by decoupling the Linux kernel from the the drivers in the Linux kernel that interface directly with the hardware from the upper layers, to make it easier to adapt new Android dessert releases with those drivers. There is actually something new in the making. I'm also here not willing and not allowed to steal the Mountain View team's thunder with announcements on doing the next step with updatability, doing the next step with Android Treble. But what I am allowed to say, and what I'm very happy to say, is that Treble not only helps updatability, Treble not only makes it easier to get new Android firmware releases on devices, but what Treble also does, and that's an intended side effect that has not been talked about a lot and that I'm very happy to go into detail here, is that Treble provides better isolation as well. Because what Treble does, based on this isolation, based on having those HALs as separate components, is it makes them their own containers. And this is exactly what we do. So every one of those single HALs that decouples the hardware driver from the operating system itself is now in its separate process, is running as apps do in separate SE/Linux contained processes, meaning that, let's take, for example, an audio HAL. The audio HAL will only be able to talk to the audio driver that is chipset specific, and in turn will only be accessible by those system components on the Android platform that need to talk to the audio driver. What the effect is from a security point of view is very clear. It increases what we call the attack chain length for a successful device exploit. It means that one bug that might exist in the upper layer Android platform components can no longer access all the different HALs and try to tap into bugs that might exist in those HALs. In turn, one HAL bug might no longer be easily used to then access code that's in the Linux kernel, that's running in kernel space, the driver code, and therefore exploit bugs that might exist in that driver code. So at the moment, attackers, with this separation in place, attackers will actually have to find an attack chain that goes through one of those supported paths that are now being strictly limited and will be more limited release by release. So this is why my team is particularly excited about Treble and why my team has put in a lot of effort from the security point of view into the whole Treble project to make sure that this separation of HALs also has a very tangible security benefit. And towards the end of my talk, I will have some more data to show that in the last year, in 2017, this actually we can show in data that this effort already improved security on modern Android devices. Now finally, and sorry about going even further into the hypothetical land here, I would like to talk a little bit about verified boot and why verified boot is actually important. Let's go back of what can go wrong. So A, malware could go onto the device. And we already have Google Play Protect, we already have Verify apps in place to make this pretty hard at this point. B, there could still, bugs will exist, bugs could be exploitable in current Android releases or in releases that haven't been patched yet. Now, C, an attacker might even still succeed to exploit that to gain root privileges within the Linux kernel. Then there's another step, D. They would have to find a way to disable or work around the SE/Linux sandboxing that's in place for their app processes, and maybe even working through an attack chain, going through the HAL separation before even being able to talk to the kernel. Now, given all those 4 steps have happened, let's assume just for the moment that an attacker is able to make all those 4 steps happen, because we see that advanced attackers can still pull that off occasionally. What is the next thing that an attacker will want to do? Because at step 4, they still only have temporarily exploited the device. They only have root privileges on a device within that same process that's running right now. So step 5 would be for attackers to try to persist their hold on the device, to make sure that they have still control over the device after it reboots. And this is exactly where verified boot comes in. Because what verified boot does is from a very, very early stage on, turning on the device, starting the bootloader code that's in the ROM mask. From that stage on, every single stage in that rather complex boot process verifies the next stage cryptographically before it is being executed. So every single stage will verify. That's easy for the first parts because bootloader partitions, etc., are small. They can be verified before even trying to execute any code on the device. For the whole system partition, that's a bit more complicated because during boot up, we don't want to verify close to a gigabyte of data before, of code before we execute it. So there actually we use the Linux kernel's dmverity feature to make sure that blocks being accessed from the flash are verified cryptographically on access. So on a block level granularity, before each and every single block is touched to load code from, this is being verified. So all of the boot up stack from ROM code to early bootloaders, of course, including all the code that runs in the trusted execution environment, and then down to including the complete system partition of an Android device is now already being verified. Android 7, Nougat, started to strictly enforce verified boot, meaning that devices with a locked bootloader that do not pass that whole chain of cryptographic verification simply will not boot. And that gives an enterprise a lot more insurance that a device, once booted and once verified to be in a correct boot state, will conform to what the system image is supposed to look like. That no persistent attacks exist on that whole chain down until the system partition. And there's even a little extra detail there that I'm going to talk about more. Travis already hinted that we support key attestation. Key attestation means that, looping back to what I mentioned about key storage in the trusted execution environment and in nowadays temper-resistant hardware, those keys stored on a device can actually come with a key attestation certificate. So there's an API, a key store API, for apps to request keys to certify that they are stored in trusted hardware components on the Android device. This trusted key attestation certificate actually includes a few other tags. It does not only include that it's in hardware, when it was created and so on, but it also includes tags attesting to the verified boot state. Those tags will tell whoever requests that certificate if the bootloader is locked, if verified boot was intact, if the full chain of trust from early on until the whole operating system was booted was cryptographically verified. And this is, again, a little bit of a sneak peek that I have not put on slides because we are still in the process of announcing the details, is that we will also be able to strengthen that towards temper-resistant hardware with Android P. So there are some more detailed changes specifically in that connection between temper-resistant hardware and verified boot upcoming. A few of those details will be announced later at I/O. And if you want to know more, I'm going to be here for the next 3 days, so please feel free to approach me to talk about those extensions that we are making right now these weeks. We've already talked now about verifying remotely that a device is in a trusted state and getting a cryptographic guarantee that the device is in a trusted state here. There's a lot of additional security measures in place to make sure that data in motion, data in transport that leaves an Android device is actually properly secured. And I think most of you will be familiar that VPN support has been built in for a long time. It is very much possible to make a VPN, to define a VPN to be always on, to make sure that all apps that are running in a work profile are only connecting through that VPN when making any connections to the outside world. And those VPN policies can, of course, be controlled. Now in Android P, there's a few improvements that I wanted to make you aware of, and those have already been publicly announced in various blog posts. One is that Android P now by default enforces TLS encryption of all outgoing connections. So if an application still needs to make clear text, plain text connections that are not TLS encrypted, it will need to request those connections very, very specifically. It will have to opt into those connections being clear text. If an app does not do that, if there's not that explicit opt-in, all those connections will by default be TLS encrypted with proper certificate pinning, et cetera, et cetera. All those security measures are, of course, in place by default. The second improvement in P when it comes to connection security is that we now support DNS over TLS for improved privacy of connections that a device makes. And of course, some smaller improvements, for example, on updating the trust anchors, updating the root CA certificates on a device. Now, bringing together those three parts, those three areas of app-based, user-based, and platform-based security, again, I will have to refer to a bit of the media cycles that happened in the last year, where it might seem that Android is insecure. We argue that all those layers of defense, all that defense in depth that we have put into place, mean that bugs do not automatically lead to vulnerabilities, and that the attack chain length is actually increasing with every single release. Pair that together with the diversity of the Android ecosystem, and these days with modern releases, it's becoming very, very hard to create an exploit that will apply to the whole range of Android devices. Or put differently, attackers who manage to find a string of bugs, chain those together to have an exploit, will find it to be very costly to adapt that chain to different firmware variations across the whole ecosystem. And that actually means that even those vulnerabilities that have been hyped quite a lot in press might not have a lot of impact in practice, to be honest. Take, for example, just stage fright. Stage fright has been talked about a lot. We have learned a lot from stage fright. Stage fright was actually one of the reasons why some of those detailed security improvements were put into place. Some of the tightening of the Linux policy, adding what's called seccomp BPF filters to make sure that some processes have even further limited attack surface on the Linux kernel. They were in response to stage fright and all the analysis, all the media reports around it. But to the best of our knowledge, we have not seen a single confirmed exploit based on stage fright for devices in practice. So that, to me, gives me confidence that all those security layers that are there actually work together to prevent bad impact from just a single layer failing. Because that was what happened with stage fright. A single layer failed. One layer of code did not parse code correctly, had some buffer overflows in there, but that was only one layer in that whole list of layers that we have put in place. And that brings me towards the end of my talk, where I'd like to wrap up and close with the statement that Android has many different security defenders. It's not only Google who invests heavily in the security of Android, but it's you in the room. From device manufacturers to SoC vendors to mobile network operators, everybody is contributing to the security of the Android ecosystem here. And there's one additional, I think, big benefit to the Android platform, which is that it's open source. By being open source, it makes it easy for third parties to actually analyze security, to actually look for security bugs. And that means we bring the academic community, we bring independent security researchers easily on board with the Android platform. And all of them help us improve security. When they report bugs, when they propose improvements to the security of the Android platform, we can take them on. We can actually improve security together with them. And this is where I think the open source nature of Android starts to really show its advantages. Because making it easy to find bugs in the source code without first having to reverse engineer binary code makes it easy for many people to do that. And although that was a bit of a disadvantage many years ago because it was so easy to find bugs in Android. And I think that open source nature actually started that negative press cycle of, oh, Android is so insecure because it's so easy to find bugs. I think now we start seeing the advantages because I believe those shallow bugs, those low-hanging fruit bugs that are fairly easy to find, we've covered a lot of them now. And we've put in more layers of defense to make sure that if another one of those easy bugs is discovered, it does not lead to a full exploit of the device itself. And that is where we see a little bit of a change here. Because other platforms that are only available in binary form first force attackers, force security researchers to go through that huge step of actually reverse engineering the code before they can look at the source, before they can actually apply some of the analysis that is easily possible in open source, that's Android. And this is where we see that based on data that I promised a bit earlier, tides have changed. We are confident enough as Google in our defense in depth strategy that we match or surpass vulnerability rewards payouts that we offer to security researchers reporting bugs in the Android platform. Mobile Pawn2Own is one contest that is well respected, that is held every year. And as you can see in the data, in the rewards payouts for Android compared to iOS, there is not a huge difference. I would say those payouts are pretty much on par. And this is one of the, I would suggest, objective data sources that we can use to compare how costly it is for an attacker to attack one of those platforms. And as you can see in that data, in the last 2 to 3 years, the security story, I think, has really changed. So wrapping up, we have tackled user-based threats, we have tackled app-based threats, and we've made sure that the platform itself is hardened and is as non-vulnerable as we can make it to bugs that might happen in code. So Android is not only the largest end-user-facing operating system in history, but right now, it's quickly also becoming the most secure. Thank you.